Good morning, everyone. Can everybody hear me? Or do I? Oh, I have one of these. So, not this one. Does this one also work? Or okay, cool, excellent. So I like using my hands for programming presentations. I don't think the speech to text is quite where it needs to be in order to make it otherwise. So I will be speaking into this guy. And if at any point during this you can't hear what I'm saying, just like throw something at me to get my attention, and I'll continue. So the presentation is available at this URL, and I'm also dynamic web page pretty much everywhere on the internet. So GitHub, Twitter, whatever. If you want to at me during it, I would love it. I'd love to hear what you think, good or otherwise. So let's get started. New. All right. So the title of this talk, as described by PyData, is around Kevin Bacon age detection. And we will do that, but it's also going to be a little bit more interesting, I think, to look at a comparative review of 3 different cloud service providers' APIs. And what these APIs do is basically give you deep learning functionality with just about 10 lines of code. So they're just like a simple call to a REST API, and you get back a great deal of information about faces, about ages, about emotions at times. So it's really interesting to see, and I think you'll enjoy it. So yes, face detection APIs, a performance comparison, and a case study. So who am I? I am Paige Bailey, and I do things with computers. I also work for Microsoft. I have about 10 years experience with Python and 4 with R. Python's my favorite, though, so I'm really happy to be here. Hadoop and Spark and all those nice little, all those nice Apache tools I've been playing with for about the last 2 years. So we're not going to be discussing them really today, but if you would like to talk about them afterward, I would be delighted. So that's about it. I'm based in Austin, Texas, but about to be moving to the Redmond area, so it'll be closer to the Microsoft campus. And with that, I hate PowerPoint. So, I probably should have started with everything in this talk represents personal views and not the opinions of my employer. But yeah, so live demo. All right. So if you go to that website that I mentioned before, pageviews/PyData NYC, you'll see 3 different links. We'll start with this first one. So I promised you Kevin Bacon, and this is a Jupyter notebook explaining just that. So everybody's seen Jupyter notebooks before, right? Show of hands. If you sat in the keynote, probably. So Kevin Bacon is a movie actor who has been around for the last several decades, right? So we have an extensive corpus of photography devoted to this great man. And what that means is that as we scroll down, we can see him all the way from Footloose in 1984 through Tremors, through Wild Things, Frost Nixon, and Contemporary. And what the Cognitive Services Face API does, this is a Microsoft product. It is available at a free tier, and after, I believe, 30,000 calls per month, you have to start paying, which is quite a bit. But what it does is you import a bunch of required libraries, so requests and the URL library, NumPy, things that you're all probably familiar with. You have a subscription key that ensures that we can track your utilization and charge you money if appropriately. You specify a region for your function to call. You specify headers and then some request parameters. And what you can see here are there are a number of options, right? So we have the ability to return an estimated age, a gender, a smile, so 0 to 1, how happy he is. Facial hair, so different types, mustache, beard, sideburns, head pose, glasses, emotion, hair, makeup, accessories, occlusion, blur, exposure, noise, lots and lots of different things. And what's feeding this? So Microsoft has a it's a deep learning framework that we've open sourced called CNTK. So you've probably heard of TensorFlow, and you've probably heard of Caffe2, and CNTK is very similar. So CNTK is what's feeding this Cognitive Services API. You request the parameters, you have the request body, you send in a JPEG, and you get back this response. So for this first picture, we have, for this first picture, that one, we have estimated age, emotions, exposure levels, values for facial hair, values for glasses, lots and lots of different things. And why is this useful? Right? Why would this be something that, that you would want to be able to use in your application structure? So the idea of using deep learning, right? You have to have engineers placed on staff, which are usually quite expensive. You have to have infrastructure, so deep learning virtual machines usually with very high-end graphics cards. You have to have an enormous amount of data, so lots and lots of information used to train. And the reality is that most large companies are the only sources for those large amounts of data. So example, Google, Microsoft, Amazon, lots and lots of classified imagery available, whereas if you're operating out of a startup, you probably don't have access to that. This gives you all of the deep learning capabilities that you would have if you had a team of data scientists or machine learning engineers on staff with 10 lines of code. And like I said, it is a proprietary sort of thing, so you do have to start paying after 30,000 calls per month. And there are 3 different service providers who currently have them, right? So why would you want to use one versus the other? And if you go to that first link, what we have is a table that I've compiled of all of the different features that you could incorporate into an API. So custom face detect is the ability to train based on, for example, you have pictures of all your employees, right? And you want to be able to specify, okay, well, we have imagery taken in meetings, video documentation. Tell me which one of my employees are in this meeting. Or if I have video footage of a hallway, tell me which one of my employees is walking down the hallway. And that kind of feels, you know, slimy yet satisfying, right? Like kind of big brothery. But that's very, very useful. And again, it's just 10 lines of code. Bounding boxes, Google has 2. Well, let's see this kind of in action, right? So we've got all of these different options that you can have for returned features. And let's look at a case study. So can anybody tell me who these 4 gentlemen are? Did any of them look familiar? Andrew Ng, yep, you got him. So this is Yoshua Bengio. That's Jeffrey Hinton. He's kind of the father of deep learning, and that's Jan LeCun. So these 4 guys, when placed through 4 different face detection APIs, this is the response that you receive back. So who has played with OpenCV here? A few? Okay, excellent. So OpenCV is not using deep learning, not at all. It's an open library from Python using something called a boosted cascade. You have a couple of options. So there's HAR and LBP, and we'll be looking at that later. So at the end of this talk, you'll be able to do precisely this, get a face bounding box, and then also an estimate for right eye and left eye. And what you see here are the responses that AWS, Azure, and Google compute for the same photograph, right? And you can see some variation. You can see that AWS has bounding boxes that aren't placed vertically, horizontally, you know, sort of perpendicularly aligned with the frame of your photo. And this could cause some complications if you have if you're using open source libraries or if you create your own proprietary algorithms. Google Cloud has a number of placements on faces. This would be useful for sort of the automatic image recognition that I was mentioning before, and Microsoft does as well. So it's also important to note that the white dots and the blue dots that you see here are only a subset of the points that are returned by Microsoft and by AWS. And the responses, if anybody's interested in seeing them, so this is the JSON response that you would get from a call to cognitive services from Microsoft. So you can see it gives you some confidence levels and some information about hair color and all that good stuff. So this is for the same photo. From Google, it looks a little bit more like this. You can see that the bounding polygons are actually, so you have the XY coordinates as opposed to Microsoft's that are giving you kind of heights and lengths instead, so top, left, width, and height. And then Google also has X, Y, and Z coordinates for every feature listed on the face as well. So left of left eyebrow, right of right eyebrow, all of those good things. Microsoft has something similar, but it's only in two-dimensional space. So it's just XY coordinates. But given that you have the pitch and the yaw and the sort of orientation of the head, you would be able to derive the Z coordinate yourself. And then Amazon, again, so they're a little bit different, and we'll take a look at this a bit later. They don't give you precise pixel coordinates, just proportions of how far it's traveled along a picture. So going back, right? Why would this be useful? If we look at the bounding polygons and the bounding boxes for this photo, right? So this first one, pretty straightforward. Everyone looking at the camera, very obvious frontal face structure. Even the open source tool was able to pick it out. So you have bounding boxes that are very similarly placed. There's a little bit of confusion around placement for eyes, but we do seem to be able to pick those out pretty well. What about these edge cases, right? So this is another for famous people, not so much in machine learning, but just in computer science. If you can name all four, I would be very impressed. But Claude Shannon is on the left, and that's John McCarthy. And these four guys are obviously not looking straight at the camera. So how did the four APIs work with those edge cases? And what you can see here, right, is that OpenCV is able to detect 3, but only with a bit of parameter tweaking. Same for AWS. Azure is able to predict the 3 on the left, and then Google is able to pick out all 4. And why would this be important? So if you start thinking about profile structures for faces, right? It is remarkable that an open source tool would be able to detect this guy and not this one. Or if you're using a deep learning framework, that it would not be able to detect this guy on the left, right? So if we move to the first notebook that I was talking about, if you wanted to roll your own API, right? So the face detection APIs that we mentioned before, lots and lots of features. So smiles, eyeglasses, sunglasses, gender, hair color. As you can see, OpenCV doesn't really give any of that. It just gives the face placement and also the eye placement. The cost structures aren't necessarily prohibitive, right? Like if you were going to hire a machine learning engineer on staff to create and support an application, you would probably be out a little bit more than $12,000 to $16,000 a month. But if you did want to try to create your own, and you would probably want to because it's fun, this is how you would go about doing it. So this Python notebook explains how to use OpenCV to extract facial images from these guys. So we've got the same photo, right? And using OpenCV, first what we do is we have to convert this from a BGR color space to an RGB color space. And what does that mean? So when you use OpenCV, it automatically converts the picture into a different format because it's a little bit easier for the algorithm to understand, the Haar Cascades classifier or the LBP. In order to display it in Matplotlib with true color, we have to change it to a different color space. For our first pass using Haar Cascades, we're going to try with the eye detection and the face detection, right? And it works out fairly well. So we've got the bounding boxes placed, but only two different eye locations. This is using just the overall eye cascade and not the right and left specifically. So if we want to get a little bit more detailed, you could use the particular right and the left eye XML file from OpenCV. And that gives us the detail that we saw before, right? So you would have the right eye located there, the left eye located there, and there's some duplication for Jeffrey Hinton and for Andrew Ng, but for the most part, you're still getting appropriate placements. And if you wanted to do parameter tweaking, right? So the thing that we did before, listed in this function, if we wanted to stress test it with the image that's not full frontal faces, then we would have to go about parameter tweaking our scale factors, right? So it was 1.1 this time. If I switch it to 1.025, and it takes a little bit to train, then we would be able to pick out the 3. But that's the highest performance that we would be able to get for this particular picture. If you wanted to try a different algorithm, so local binary pattern as opposed to Haar Cascades, this is what you would do. And the highest performance that you can get is still just the 2 central figures as opposed to all 4. The Haar Cascades profile classifier also only picks out Weizenbaum on the right. So these APIs, the level of detail that they're able to show is only possible through deep learning. Right. So if you wanted to create your own algorithm for face detection, it would be quite simple. If you wanted to do it for something a little bit more nuanced, so the propensity for eyeglasses or sunglasses, gender, hair color, whether or not someone has eye or lip makeup, those sorts of things, you would probably either need to use a deep learning framework or you would need to use one of the proprietary APIs. So for the Kevin Bacon age detection, right, why we're here today, what we found after executing each one of the pictures is that the classifier is a little bit biased. So scrolling down towards the bottom, you can see that the actual age estimates, so 26, 32, 40, 50, 59, differ substantially towards the edge cases for the actual age, right? And why would this be? And it would probably be because of overfitting. When you have a training data set for deep learning, it's only able to give you information about the data that you feed it, and the data set that's been fed into the algorithms for CNTK, for TensorFlow, for any sort of deep learning framework. They're mostly focused on ages 20 through 40 because who's building these things? They're programmers, right? And what are their age demographics? They're mostly 20 through 40. So as you get out to especially younger ages or upper ages, you're probably going to have differences. It's the same for movie actors, right? So why would this potentially be biased for Kevin Bacon? Maybe he's had some facial reconstruction done. Maybe these photos have been retouched in Photoshop. So the accuracy of the ages vary based on input, based on situation, and then based especially on your training data. If we go back to the comparative performance of the APIs. So we mentioned a perk of Google, right? Google gives you XYZ coordinates that can also be derived through pitch and yaw and XY coordinates that are available through Microsoft and also from Amazon. What about ages? And what about emotions? So age estimates for this guy. Kind of elderly gentleman on the left, a little bit younger on the right. If you look at the actual ages in April 1968, Ed Fredkin's 34, so he's the guy that's very obviously smiling. Claude Shannon's 52, McCarthy's 41, and Weizenbaum's 45. Amazon and Microsoft are the only two APIs that offer age detection, and the accuracy of each is kind of displayed over here. So what this is doing is it's taking the JSON response that you saw in VS Code, so the face details with the bounding boxes, the age ranges for Amazon, and then for Microsoft, the age ranges that you see down here. So I believe it's up towards the top. And it's pulling in a confidence interval. And if you're familiar with statistics, I'm assuming this is kind of like a 95% confidence interval for the actual age estimation from Amazon, but the spread is huge, right? So you have a variation of like 20 plus years for each estimate, which isn't really telling you much at all. The cognitive services estimation doesn't give you a confidence level, but it does give you at least kind of a floating value for what it assumes the age to be. And like I said, Google doesn't really offer that. In terms of placement for certain features, it offers quite a bit, but for age ranges and for emotions, not so much. So happiness, right, or any sort of emotion detection. How happy would you say this guy is? I would be, smiling. Seems to be smiling. Seems to be pretty joyful. And for the face API attributes, it seems to be pretty confident that happiness is a thing. Google returns very likely, very unlikely, very unlikely, very unlikely, very likely for the 4 different emotion options. Amazon recognition has 3 options, so confused, disgusted, and also happy. So those are the only 3 options. And it doesn't seem to be very clear, right? So it's 52 to 62% confident that this gentleman right here is disgusted and confused. Not quite. The different emotions that Microsoft offers are, again, anger, contempt, disgust, fear, happiness, neutral, sadness, and surprise, which is pretty extensive. There's also the option to pick out whether a person is wearing eyeglasses versus sunglasses versus goggles, so some sort of sporting equipment. There's the ability to detect sideburns or actual beard or a mustache, and the ability to also detect certain accessories like hats. That's listed up in the table. Here. You can see that in like I said, in terms of the accessories, the emotions, sort of the people information, the things that make a person tick, Google's not quite as capable. AWS is also a little bit behind. And the shorthand here is conf, stands for confidence interval. Percentage is kind of giving you a percentage value as opposed to a float. And then X just means that it's available. And then the final cells down here are related to facial landmarks and orientation. All of the facial landmarks seem to be placed in about the same area for the ones that are present. Google and Microsoft give you precise pixel locations, whereas Amazon just gives you a 0 to 1 value on how many pixels it's traveled across the photo. And this shows you how you would go about creating the Z coordinate for pitch and yaw, and XY, if you have the others. And then, everybody's always concerned about costs, right? So AWS is listed in blue here. The gray is Cognitive Services, and then the orange is Google's API. So that is all I have. Has everybody been following along? Does anyone have questions about OpenCV or about any of the APIs that we've seen here today? The REST API calls are all very, very similar to the one that you saw here for Cognitive Services, right? So you're just importing libraries. You're defining a subscription key and a URL to base your region. You have headers with specific parameters, and then you just end up executing the API call and getting back the JSON response. Yes?
Who are your most common customers?
The most common customers for this guy? So the full extent of APIs, right? So Cognitive Services, Microsoft. The full extent of APIs is everything from vision to speech to text, sentiment analysis to search to language. So we have about 35 listed. If you would think about use cases for this, right? So Snapchat, the filters where you have the weird dog ears and the nose and the sort of smiley faces that can be masked. You can create that app very simply using this Cognitive Services API or any of the others that I mentioned, right? Because you would be able to detect automatically where pupils are located, where mouths are located. That would be kind of a fun use case. There's also obviously the feature that I mentioned before, right? So if you're able to detect a specific human being, then obviously that would have a lot of customers in government and military and even, sort of business settings. It also would be kind of a nifty extension to LinkedIn, right? Like if you were able to walk around in some sort of an augmented reality situation and detect, oh, well, that guy Joe is the vice president of whatever company. I should probably go and talk to him about something, that sort of thing.
Has anybody ever used it for product testing or anything like that?
So that would be very useful as well, or detecting if someone was falling asleep at the wheel, right? So detecting sort of eye gaze about paying attention. There's also a use case that I heard of where, so movies, what they do is they send laptops with films preloaded to potential customers. The customers then watch the movie and sort of give feedback back to the company on their opinions. But what this would do was it would be able to detect that it was just that single person watching it, so not anybody else. It would also be able to detect attention spans and emotions as they watch the film. So you would be able to see in real time tracking whether or not a person was disgusted or happy or angry, their precise emotional response to that particular extent of media. So that would be useful as well. Yes?
So while this is for face detection, Do you have any, by the way, this is a great study, I thoroughly enjoyed this. Is there anything similar like this to, for face matching?
Face matching, yes. So that's what I mentioned before. Unfortunately, Microsoft. Well, I guess maybe fortunately, Microsoft's the only API that offers that. OpenCV does give you the ability to do sort of eigenface matching, but you would have to provide your own data set and train it. What you would do, the way that it's structured in code is you would have a directory with a number of pictures, 5 to 100, however accurate you wanted it to be, of a particular person. And then you would just kind of point the API towards that folder and be like, okay, well, if you see anybody that looks like Paige in any of these photographs, tag it as Paige. And out of the box, Cognitive Services and Google's Vision API are able to detect celebrities. So if you stick in a picture of Natalie Portman, it's able to detect that it's Natalie Portman. Or if you stick in a picture of Kevin Bacon, it detects that it's Kevin Bacon. And again, the entire motivation is kind of giving you all of the tools for a deep learning task without you having to learn TensorFlow or learn CNTK. Yes?
So I'm curious, for Microsoft, that custom face detection, how does that work? Do you have to train it on your own set as well, like OpenCV? Or
Yes. So you have to train it on your own data if you want it to do like a corpus of your employees. If it is just celebrities, so things that the internet would know, then you don't have to train it at all. Yeah. Yes.
I imagine there's like huge variance around what a 59-year-old face looks like.
Yes.
So the case, like, we thought that underestimated Kevin Bacon's age, but they actually made it like it's 48.
Yeah.
Are those point estimates for the age ever useful in that sense?
So sometimes they are, but mostly in terms of detecting minors, right? So another use case would be, say you have a website that you don't want a 13-year-old to be accessing. You want to make sure that the person is adult, 18 plus. It would be useful to have, your video camera take a picture of that person's face to detect their age for a given threshold, and then use that to say, okay, well, you have access to this site now. So I would say that, like, if you're looking for extremely high accuracy, probably not. If you're looking for a general estimate of whether this person is young versus college age versus 30s to 40s versus elderly, then it would be useful for you. Yes. So if you give me usage keys, I would absolutely do that. It's the same for anything, IBM Cloud or any of the others. The only reason I was able to do these estimates that are listed in the table here is because I used the free tier for Google and for AWS, and OpenCV is obviously also free tier. They do? All right. Clarify, I will add to the list. But in general, like I said before, each one of these guys has strengths and weaknesses. Google's gives you XYZ coordinates out of the box, but you can always derive your own. It's also the best at spotting faces that are more in profile, though Claude Shannon was detected by Microsoft and Google both. In terms of emotions and age, that would be probably Microsoft bringing up the head, and then also the ability to detect things like beards or mustaches or sideburns or different sorts of accessories. AWS has a little bit of wonkiness in terms of sort of pixel placement. Like it would be very difficult to sort of incorporate that API with multiple others. And then it also doesn't have as extensive as a listing for the particular feature landmark locations. So that's what you get for the amount of money that you would pay for it. That is what you get. And free tier for the different tools varies. Google is it gives you several thousand per month, I believe, or maybe 1,000. AWS is 5,000 calls per month. This is 30,000 per month, and OpenCV is obviously very free. So excellent. And then I also wanted to mention a note on deep learning in general, right? So the three APIs that I mentioned, they all incorporate some sort of deep learning. So CNTK versus TensorFlow versus whatever AWS is using. But the reality is that it's very, very easy to fool a deep learning network. Right, so what you see here is an example from Clever Hans's blog. If you're interested in adversarial machine learning at all, I sincerely recommend looking at it. What this is, so does everybody agree this looks like a panda? It's pretty panda-like. Looks like it lives in a tree and it eats bamboo. TensorFlow is 57.7% confident that this is a panda, that this image is that. If you introduce 0.7% noise, so just 0.7% of data added to that picture. What you get back is an estimate that this is a gibbon with 99.3% confidence. A similar feature would be that you probably saw that thing floating around Hacker News recently where a turtle was mistaken as a gun. It's the same general idea. If you deep learning networks are so very easy to fool, and it's mostly because they've been kind of hyper fit on these particular parameters with their backpropagation. There's also a recent paper done for 1 pixel attacks for fooling deep learning networks. And this is an estimate of how these guys were misclassified. So this is an airplane that was misclassified as a dog with just 1 pixel of noise added. A dog that was misclassified as a ship, all sorts of things. And so if you're architecting your own deep learning systems, I sincerely recommend considering how this sort of bad actor activity could harm your deep learning models. Because if they're misclassifying, that would be potentially hazardous. Right, like if your company is in the business of detecting where missile locations are in satellite imagery, and a bad actor is able to introduce 0.7% noise that suddenly classifies it as a place that's safe, then that would be a bad time. So you will overfit. There are 5 stages of grief. I suggest you look at them. And that is all. So thank you.